didn't move. I don't understand. Hello, we're live again here. Getting this correctly is challenging here. And not having the computer fall off would be bad news. It's good enough. All right, so we're back again here. I don't know if I had time to watch them all. Nope, I can't do this very well, can I? There we go. So what we're going to do in this one is way more math, and I have students who've already practiced these questions. They're behind me. So we're going to go pretty quickly. I wrote the questions just on some paper. So I'm going to do first is just have you write these down and try them. So if you were to watch this or rewatch this or something, I would write this question down and then do it, and then watch us kind of go through it. So here is the question that we're going to do first. It has to do with an empirical molecular formula. Oh, nope, we're not doing that one first. False alarm. This one. So we're going to do the easier one first. We're going to find the empirical formula for that. This is something that we do in first year chem, but typically I don't review it in AP. So now we are. And then here is the second one. This one's much harder. And this one you'll have to do an empirical and a molecular formula, and it's a combustion. So there's lots going on with this one. To me, this is super likely for the AP exam, that one, especially on a multiple choice. This might be, but I haven't seen this actually show up in a while, but it could have shown up on the multiple choice and I wouldn't even have known. So the combustion way to find an empirical formula. The other thing we're going to do is we're going to do a solution calculation also. So a lot of math this time. So you're just going to see me kind of going through the problems. So let's just get started. So my students are just going to check. They're going to help me out because they've already done this problem right here. Okay. So we've got a compound that contains carbon and hydrogen and oxygen. So you'll see your chem teacher probably go C, H, Y, O, and then Z. So they'll say that got that. Okay, that's how you should start. If you're trying to get all the points showing your work, there are some faster methods. I'm probably going to do a pretty medium length method, but you do still need to show mole amounts and how you got them. And I always tell my students number, unit, label. Okay, so we know this about this substance. It says it's got 48.64% carbon. It's got 8.16% hydrogen. Is that correct, you guys? And then they don't tell us the oxygen, do they? So I try to pick kind of an easy to medium one for AP. So what do you do? How do you find the oxygen? It's pretty simple, actually, if you know it. You just subtract from 100, right? So my students already did that. What did they get? Was it 43.20? Fantastic. Okay, so they basically said that has to add up to 100. There they go. Now, the next method is, I think, a slower method than some, but I still like it. So what I would do then is say that those are the masses. And so a lot of times on the AP Chem exam, and I'm going to do kind of a newer method, which is like a fence post method. I used to do the times and the arrow and not arrow, times and then the parentheses, but I like this now digitally. So what do we put at the bottom? I want to turn this into moles. On the AP exam, it's really common that you will get points sometimes for just showing the mole amount of something. So let's get the mole amounts of each one of these. So if you want to go fast, I wouldn't use the 12.01. I would just use 12. You're probably going to end up close enough anyway because it's a lot of estimating anyway in the formula. So save yourself the time and just divide by 12. What'd you guys get? Or if you divide it by more accurate, that's fine too. 4.05. Great. So my students, like I said, I've already given this problem before we started taping. So they're going to help me go fast here. So then 8.16 grams of hydrogen. I would just divide it by one hydrogen. This is the one you probably don't really want to show, but you still should. So it's 8.16 moles of hydrogen. And then last, I can do that without them helping me. And we're not going to really worry about significant figures here. I would just use 16 for oxygen per 1 mole of oxygen. And then what did that one give us, you guys? 2.70. Okay, so what I saw somebody do one time, and I love it. Okay, now don't do all this on the AP exam. You need to get out of the question. But I think for learning purposes, what we would do right now is we would say it's 4.05 carbon, it's 8.16 hydrogen, and it's 2.70. That's why we're not done. Okay, so I saw somebody else do that sometime in my teaching career. It's been 20 years now. So I was like, well, that's a pretty creative way to show why we can't stop here. Because that's ridiculous. That's not what a formula looks like with decimals, correct? So what do we do to get rid of the decimals, even in just math? Divide them all by the smallest. So you just take it and quickly divide by the smallest, giving us 1 And then what did you guys get for the other ones here? This one, carbon is 1.5. Oh, we're so close. And what about this one? 3.0? Okay. How are you doing, Dane? Does that look right? Okay. So then we're still not done, but let me do this again. Do not do this on the AP exam. It's just kind of wasting your personal time. But we're getting close. We still can't say we're done because we still have the carbon as a decimal. So then, here's crazy. What are we going to do then to get rid of the decimal? Really easy again, it's math. Just multiply them up by something, which in this case is kind of nice and easy. You just multiply them all by 2. So then that gives us, I'm going to put this down here, and we're done. So it gives us a quick formula. One of my faster calculating type students said he did this question, I think what he said, under 2 minutes. So it's a good multiple choice question to get your points on, probably. I might show up on the FRQ. What did we get then? So then C3H6O2. And then before we leave this question, I kind of thought to my students when we went over this, it's cool right now to throw in isomers. So isomers really aren't part of the AP exam, but they kind of are because they show up. So this is a good example of a molecule that you can connect many different ways and get different answers. So we just kind of found 2 common ones that you might have been able to, if you had, it's 3 black ones, those are the carbons, the circles that are black, model kit. 6 white ones and 2 red ones, if you get to just play. You could build these 2 structures, and I'm going to pick on Josh one last time, Josh, I promise. Because I think this would be good for Vesper theory again. Does that look right, you guys? And what do they call it? Propanoic acid, I think. So there's 3 carbons, so you can connect it. You've got basically a 4 region here that's bent. You've got a 3 region here that's trigonal planar. 4 region tetrahedral, 4 region tetrahedral. So you could do polarity even. This would be a polar molecule because of this basically this bent end of this molecule and even the oxygen here. So that means it should be soluble in water and all the fun stuff that goes with being a polar molecule. Could you have dipole-dipole forces? Of course. Could there be hydrogen bonding between this one and another one? Yes, but you got to draw it right, okay? So if you were to try to draw like let's just pick on water. If you were to try to draw a water right here and say that this was a hydrogen bond, I'm off the screen, that is not a hydrogen bond. Here's why. This happened on the AP exam. I forgot to say this last time. Josh, hear me now. This is a carbon right here bonded to a hydrogen, attracted to an oxygen. So it doesn't make the cutoff. It has to be fluorine, oxygen, nitrogen bonded to a hydrogen, attracted to a fluorine, oxygen, nitrogen. So this right here, you could say this is a dipole-dipole, but you can't say that that is a hydrogen bond. The last choice would be, well, what if I put it over here? I put a water facing like this. Lone pairs like that. And then if you said, well, here's a lone pair, it's not bent, but it is in 3 dimensions if you were to draw it correctly, that would be a hydrogen bond because I have an oxygen, hydrogen, oxygen. So this actually could be the dipole-dipole hydrogen bond force, but we probably say just hydrogen bond. Whereas this one, you would call this one just a dipole-dipole, okay? There's one other way you could connect this molecule. We put it up here just to show you the difference. It's kind of similar. Oh, I got rid of it. Let's see if I can remember. Is it this? Hopefully this class can remember. Nope, there's an oxygen here. I think it was called methyl. Oh boy, testing my memory now. It looked like this, I believe. Yep, so you've got 1, 2, 3 carbons, 2 oxygens, and 6. So that's a different molecule, and it has still probably some polarity, but it's very different. Okay, so those are basically what are called isomers, different than resonance because we're connecting them differently. Okay, all right, off to the next one. So the next one I showed you was on that bright green paper. It was that cumin. This one took my students a little bit longer. I think this might be a little too difficult for the AP exam. If this wasn't a live video, I would cut out the fact that you have to watch me erase the board. That's kind of boring, huh? Okay, so we're doing, well, there was actually there. I did have it there. So we're going to do this one. This one's going to probably take you a little longer. So we have this thing called cumene. And the only thing we knew was that it was only carbon and hydrogen. So that was kind of nice. We knew we only had those 2 elements. Here's the harder part though. We combusted it. So we didn't do any chemical reactions, and I'm not sure if we will. I really feel like that might be something that we can work into these next questions. So combustion of a hydrocarbon means we're going to put it with oxygen. It only hydrocarbons, hear me now, only hydrocarbons, carbon and hydrogen and oxygen containing things, will produce CO2 and water, okay? Don't mix up the fact that if you were to combust, let's just say gas. If you were to combust magnesium, okay, that does not produce CO2 and water. I know you're going to say, well, are you kidding me? People write that. Yes, they write that, okay? So magnesium will just produce magnesium oxide if you combust it, okay? So be careful. So combustion of a hydrocarbon. Now, we can't balance with mole ratio because we have no idea what the X and the Y are, okay? So here's what the problem told us. We burned 47.6 milligrams of this, maybe in some kind of thermochemistry environment, and we knew we produced 42.8 milligrams of that. And then they probably just said, you know, some excess oxygen. Do we not know that one? So where are we at here? We didn't know the oxygen, right? Some excess oxygen. So this question actually makes me kind of question how we. Okay. So what I'm going to do is be very careful. My students solved this, but I'm thinking we can't just use the law of conservation because we have no idea how much oxygen we combusted. So we really can't find this mass at this point, okay? This is a really hard problem. Do you guys think you've got the right answers? No? Okay. So we're going to have to work with what we got. So all we know, and I tell my students, think of this really logically, all we know is that this carbon, okay, I'm going to put it in blue. So how's that look? Not too bad. Goes here. Okay? Shade it in. So we know that the carbon goes there, but we don't know anything about that carbon. And even though we said excess of this, we still don't know the mass of this, and we don't know the mass of this. We can't do the law of conservation. Okay, you can't. This is a hard problem. I think this one's probably a little too hard for the AP exam, but let's keep going. So then the hydrogen, I don't know if orange is going to show up. Okay, bubble letter these suckers here. Okay, this hydrogen here, how does that look? That's not bad. Turns over here. So let's focus on that first, okay? I think I might have picked a problem that's too hard, but we'll work through it. So let's just focus on what we know, okay? So of this 42.8 milligrams, some of it's hydrogen and it came from here. So what do you guys think for some advice? What should we do? We picked a too hard a question here. They're kind of looking at me like, I don't know, you tell me. So we don't know the formula here, but we do know that 42.8 milligrams is the H2O. So the first thing I would do is get rid of the milligrams. Those are the 1,000 milligrams in 1 gram. So this is where let the stoichiometry kind of guide your way. What do you think we should do next? I'm actually going to get where I put it. So what can we do next? Yeah, we can say that for every 18 grams of water, there's 1 mole of water. Are we okay with that? So we're just kind of I always say to my students, let the units guide your way like a map. I'm actually just going to make sure we don't head out the wrong direction. So they found the first one pretty easy. This one actually might be, like I said, a little too challenging, but we'll still go for it. What can we do next? Because we were trying to find the hydrogen. Oxygen, man, don't try to worry about the oxygen at this point. Number 1, it's not part of this formula. And 2, oxygen is a reactant that we don't know anything about. It's a product we don't know anything about here in this carbon dioxide and in this water. So stay away from that one. All right, so what question is this? Okay, so make sure I got the right thing. I know what we're doing here, but I'm trying to let them think, and I'm letting you guys think too. Well, what can you do next? Yeah, you can do like a mole ratio, okay? So you could say that for every 1 mole of water, You could do something. There's a couple methods at this point. You could say that there are 2 like moles of hydrogen or 2 hydrogen atoms, so you get like a doubling effect there. All right. And then what do we get if we just kind of stop at this point? And if you want to go back to milligrams again, we can. I think I'm going to just because that's what this has. What do we have as it, check your numbers here. So if we stopped at this point, we'd have moles. I'm not sure we want to stop at this point, or do we want to stop at this point? A couple choices. Want to try it? Okay, want to stop at moles? Let's just see, because this is where you can go. There's a lot of different ways to handle this. So what did we get here? Okay, so 4.76 times 10 to the negative third. Okay. So I'm going to leave that there. We could turn that into grams and milligrams. I'm just going to do that just to see if it gives you an idea. So this is just the hydrogen though, right? All by itself. And if I have 1 mole of just hydrogen, this is not going to be diatomic in this case. Be careful. It's 1.0 whatever grams of hydrogen. And then I'm just going to do this just to see if it gives anybody some ideas. You can always just stop at moles here. So you have 1, let's see, 1 gram. Oh, not, yeah. Oh, yeah, I'm not 1 gram is 1,000 milligrams. I forgot we're dealing with milligrams in this problem. So this, what would this milligram amount be? And this just gives you options because this is a tough problem. I think I went too tough, but that's okay. We'll keep going. It's a good stoic review. Yeah, 4.76 milligrams. Tiny. Does that fit on the screen? Barely. Okay, so I'm just going to write that right here. 4.76 milligrams. So that was the end result way over there. That's kind of small to see. Now, does that give you any ideas, though? They're getting there. Maybe some of you in there are kind of, ooh, okay, now I got a number I can kind of mess with. Because where did the hydrogen come from? Here, right? So you do have the law of conservation that all of the hydrogen that would have been in this mass did end up over here, in that right there. So what's kind of your, you might have some ideas. Remember how small the percent of hydrogen typically is. There might be a lot of hydrogen in a molecule, but they don't weigh a lot. So it's okay that that's such a small number. So what are some ideas you guys are having already? I think some people, there's 2 routes you can go. I know where I'd go. That means this 4.76 milligrams of this mystery came from there. So what could we do? Yeah, we could subtract these 2. Because then what would that give us? I heard it. The milligrams of the carbon. And we're sort of totally ignoring the oxygen at all, saying you are just everywhere. You're always a problem when it comes to combustion. So what is this mass? So 42.84 milligrams of carbon. So what can we do now? I think this one's too tough, but it's still good to review. I think this one really pushes you to the edge. Can we turn that into moles? Yeah, we could. So I'm going to leave this mole out there because, like I say, leave your numbers. You never know when it might be helpful. So again, there's 1,000 milligrams in 1 gram, and then let's just say that we're dealing with carbon, right? So there's 12 grams in 1 mole, and we don't have to do this because we already know this is just the carbon. This is where that number unit label will sort of save the day. I want these 2 moles to be sort of near each other. What is that mole amount? And again, there's more than one method to solve this problem. I like this method, though. I like the way you guys are going. It's going to be small again. Anybody get it?
3.57 times 10 to the 3rd.
Great. Now, just like the last problem, what do we do with these mole amounts? So let's just stop right now and put them into what they are. So we would say we have C and then 0.00476. No, that's not right. That's the other one. So this is silly. Don't do this on the AP exam. I'm trying to help you guys make sense of it. And I always tell my students, like, we don't use a mole of something because it's a lot. So that's a true statement. Like that's the mole ratio of those two. But you know, diggity dog, that does not look good. Okay, that's not gonna be what we can say. Okay, so what do we do then? Divide by the smaller one. Okay, so who's smaller? You can even do it right here. This one, right? What did we get? It's not going to be, I don't think it's going to be great yet. We're going to get 1, but I think we're still going to have kind of a mess. Bless you. What did we get? They're checking because they did this one kind of ahead of time, but not really. And I'm letting them just check it.
Like 1 and a 3.
Okay, that's okay. So 1.3 repeating kind of thing. That's okay though. What can we do to get rid of like a third? Multiply it by 3, and we're going to get C3H4. And then we're not done yet. I hope this was the right answer. Oh, we're good. I checked it. But we're not done yet, are we? We're pretty close. What is this called? It's the lowest ratio of all of the elements in a formula. This is the empirical. Okay, now this question had one more step up. This is a good one, but it's, I think, a little too hard. Unless they throw this on the multiple choice, a lot of times they tier it, and the hard multiple choice math questions are in the middle. I can't say they can't put it on there. It's not beyond what we can do. It's just this is some time consuming. We're at like 21 minutes. I don't know how long it took us to do the first question, but this is an investment of time you might want to, put your time into. Okay, so what are we going to do now? Well, they told us one more thing. Here was the thing. Okay, they said that the molecular mass was somewhere between 115 to 125. So what are we going to do now? So now we know that this is actually possibly C3H4, or we go like this, or some, I'm going to put like times W, or some multiple higher than that. Okay, so how do we know if we're done? Trying to find a good space to go here. Find the molar mass of this, right? I think we can just sneak it over here, right? So what is this way? So it's 3 times 12, really simple, and then 4 times 1. About 40 grams per every 1 mole of this one. But ours is supposed to be between 115. So this actually is between, so this isn't it, obviously, right? So it's between, I don't even know where to go. I think I can go right here. Yep, but this is enough room. So we take like, let's just do 120. Are you guys okay with that? Because it was 115 to 125, Nathan. Because why did I do that? You probably figured it out, right? Divide by 40, right? That equals 3. So I took the molar mass, kind of estimated it, picked something easy. So that means instead of being C3H4, it's actually so tiny bit of math quick here. So it's actually C9H12. And I thought we looked this up too. We know like this is the right answer. We looked in the back of the book or whatever. And then we looked up on the internet what it was. We looked up this cumene order. So we're good. Okay? That was a hard one. A little sweat working up here. Again, if this wasn't live, I'd probably cut this out, but I can't. How are we doing though? That one's like a lot of stoic, little bit of balanced equation, but we couldn't balance it. But we did predict the product, sort of, we needed those. And we never really worried about the oxygen, and we kind of found the carbon indirectly. And that one's probably a little hard, but it's a good review. All right, moving on. We're going to do one more. For sure. We're going to do a solution calculation. So I'm just going to kind of read it to you. Oh, I got to go back to where it was. Let's go for it. There we go. So we are going to do, let's see. We're going to take, I love these words, a 100 mil aliquot. That means they came out like a pipette and they measured it. Don't worry. 0.2 molar, aqueous or aqueous, potassium hydroxide. So let's just write that out. So you have potassium hydroxide, AQ, and what did I just say? 100.0. Add that in there. So you got 4 sig figs with this thing. And then it was 0.200 molarity. 0.200 molarity. And then we're going to add it to, what does it say? It's mixed with or added to 100 mils of 0.2 again, magnesium nitrate, and again, aqueous or aqueous. So magnesium is a 2+, nitrate is a 1-, so you're going to need that. So we're kind of covering some basic reaction prediction and writing and compound naming all at one. That's really what you should do in AP Chem. You really shouldn't, go back and say, can you guys write magnesium nitrate? You just kind of have to assume your students can do that. And if not, you got to hold them accountable in first year chem. That's just my piece of advice for any teachers. So what are we going to make? And then we'll do a net ionic too, because the AP test wouldn't want this molecular equation. They'd want the net ionic. So what do we get? So potassium, theoretically, is going to try to switch places and bond with that one. And 1+, 1-, so we're good. And then the magnesium is going to, again, try to bond with the hydroxide. And it will be successful. I'll tell you why in a second. But magnesium is a 2+, hydroxide is a 1-. You need parentheses around that because it's a polyatomic ion, and then 2. So how do you predict states of matter? And then we'll balance it. So my students should have a foldable. I don't know if anybody has their reaction foldable handy. But for sure you need a solubility chart or rules. I kind of like the charts, although there are a lot of errors on the charts. Let me go grab them. I'm going to pass that one up here, Abby. He's got it. So they have a reaction foldable. Eek. Okay. So on here, they'll have all the types. On the back, they have their solubility rules. I think the newer ones, I even have a chart where they put, they do ionic reactions right here. They'll have a chart inside and notes and stuff. And then we're doing a double replacement right here. So then they'll have all the examples of doubles on the inside. This is not a special double. This is a normal double. We'll talk about the special double before I hit end, which is if we produce carbonic acid or ammonium hydroxide. Okay, remind me, or sulfurous acid. So it's not a special double. It's just a normal double. Crazy special about this one. Okay, so what are we going to do? We have to look up that this is the solution, and this is the precipitate. Now, magnesium hydroxide has slightly soluble stuff, so it could be that KSP. These first 6 videos I'm making, because again, they're, 6 total hours? I think maybe later or next year I'll make, the other ones on thermochem, kinetics, equilibrium, all the jazz. But right now, we're just focusing as our needs, right? The students that are sitting in front of me. Our needs are going back to reviewing the easy stuff. And Josh, we have to fill the holes he has. Okay, so it's really about us. So moving on. So what are we going to do? We have to balance it. So in first year chem, I actually balance with a different color. I'm not going to do that right now. What's the balance equation, you guys? 2, 1. I like to put the 1s, 2, and 1. Now, before we even go on to the math, we're going to go right to the net. We're not going to do a total. You would say that really what's happening is 2 hydroxide ions from here in solution are going to react with 1 magnesium ion in solution, where we're taking out these spectators, the potassiums and the nitrates, and they're going to produce the unique change as a precipitate. You might even have some teachers in the good old days would draw a little arrow like that. That would mean precipitate. Otherwise, there's some teachers that will say, no, that's the PPT. That's the precipitate that we're going to make right there. For the solid as a precipitate. And we make 1 mole of that. That's going to be important. Okay. So I'll end up having to erase that because I need that room, but make sure that you can do a net ionic easily. Those are the ions that matter. And then if you were going to do KSP, the only thing I'm going to quick remind my students is if we were going to do KSP, you would go and do this. So you kind of handle it from the perspective of the precipitate is already made, and it's going to have in equilibrium with the ions that it might produce at a certain temperature, and you can look up all that data. Okay, so this is where it kind of ties in first year to second year chem. So this would be later in the year or later in the review. Okay, I do got to get rid of this because we're going to need that special room, but I need you to think about it. So what you can do is a couple things. You can find all concentrations of all ions immediately, or you can just kind of progress and figure out what you want. First thing that this question wants is what's the mass of the precipitate? So let's just do an easy stoich just to do that. And pretend like this is the only thing the question's asking you. Pretty likely, I would bet. I would think on the multiple choice somewhere they would ask you to calculate a product's mass. So I don't know if it'll be double replacement precipitate or something else. Okay, I got to take some tea though. And I'm giving them time. This cumin question, wow. I gave them like about 10 minutes or something to kind of get a head start. And then I'm like, we're going live. So they had a hard time with this one. So I think right now they're working this one right now. Or Josh is like, I'm just going to wait for you. You can do it. Okay. I should just wave. There's nobody watching us. Well, no, that's not true. Somebody watched the other one already. It's probably Michelle. Michelle, when you watch this, hi. I think that is pretty likely. Your DECA people. Maybe you're on the plane and you can't watch it yet. See you in Florida at Harry Potter World, right? Is that what it's called, Harry Potter? By the way, they didn't just go to nationals. It was internationals. Canadians are there, I guess. Okay. And I think some people from China. I don't know. Okay, here we go. Let's just do this. What do we got to do? Oh, no. Limiting excess, right? So I'm just going to approach it from that aspect. So we're going to say I got 100 mils of both. Some of you in AP Chem are going to be way faster at this, but I'm going to show all the work because there might be some people who are struggling here. And we're going to do number, unit, label. This is this one. So that's going to be the moles of KOH that I have. And again, there are going to be people out there that are going to say there's faster ways. I'm going to even tell myself as I thought about this right now, my disclaimer on the last video, say this quick to the screen here. Happy to have Dana in class here too. So the last video, by the way, intramolecular forces is just something I kind of came up with. It's sort of in books too though. But really when you have an ionic bond and a metallic bond, it's not a molecule, but I kind of throw it in there. Okay, so just, it's okay. Don't worry about it. But call it an ionic bond or metallic bond. But I just say it's like an intra kind of force because I want it compared to an inter force. But you really have to be a molecule. And Dane and I talked about the only thing that's a molecule are covalent things. It's fine. Okay, so if you're watching these, just don't judge me. I just wanted there to be two camps. Okay, are you a bond, which I kind of call intra, or are you a force between molecules, which is inter? Okay, that's a little disclaimer. Moving on. Plus, I gave you guys some time. What do we get as a mole amount? They're both the same, right? Point.
Oh, wait, it's divided by O2.
O2, right? That's what I thought. Now, Dane, I'm not going to worry about the sig figs till later, okay? I just want to save some room. So he's going to be like, that's only one sig fig, and we really could have kept 3. Just, I'm going to worry about that later. He's going to catch me on it the whole year. It's good. It's a good reminder, though. So I'm just going to, just to save room on the screen here, I'm going to put the labels, though. Now, you really probably know who's limiting and who's excess, but let's just show it quick. The key here is, I'm going to unplug this. Hopefully it's all fine. Oh, well, maybe better not. Where again, I think I begged for 1,000 subscribers because then I could use my phone, which would be way easier. Okay, so we already know who's limiting, but let's just prove it. So the mole ratio is that for every 2 moles of this one, you need only 1 mole of this one. So, you know, here already you're kind of proving which one's going to run out. But I think you want to have these mole amounts. And if you're suspicious you know who it is, then you only do 1 of these. So divided by that, I only need 0.01 moles of the MgNO3. Okay? Are we okay with that? So do we know who's limiting, who's excess? It's important. So we have extra of this magnesium nitrate. This is all a true statement. Okay. So here's what I want you to do right away if you had this type of question is make a spot or make a box. So it would be somewhere. And it depends on what they're asking you. Right now, we just want to find the mass of this, okay? But I'm going to go to one more step beyond this just because I think it's good review. Is it going to be on the AP test? I have no idea, but it's good review to kind of keep you thinking. We are going to calculate the concentrations of all ions in solution. So don't forget to do this. Over here on the side, we're going to do the precipitate right now. That's the easy one. We are going to calculate the concentration of all ions in solution. So there's 4 possible ions we have in solution. We have potassium, hydroxide, nitrate, and magnesium. Okay? One of these concentrations of these ions is 0 molar. Meaning it's completely consumed, and I'll give you a hint, it's in the precipitate, okay? And then 2 of them are spectator ions where they didn't do anything. Whatever their concentration was at the beginning, it's the same now as the reaction progressed. I'll draw a particulate view in a second. But let's just do the mass. And then the other one is the harder one, okay? So let's just keep going. So this is how many moles I would need. So I can do a couple things. I'm going to start with my limiting, which is this one. So I'm going to say that for every 0.02 moles of KOH, I would do again that mole ratio for every 2 moles of KOH. I'm going to get 1 mole of MgNO32, okay? Which is going to be the same answer. So I'm just going to transfer this down except for, oh no, MgOH, okay? Sorry. Same mole ratio though. So 0.01 moles of MgOH2. My apologies for this being messy now. And then what do we do next? For every 1 mole of that, we would do its molar mass. So who's got it? We're in chapter, this is technically in our book, I think a chapter 4 question, isn't it? So that kind of put them on the spot here because they had to do this one quickly. Because I gave them such a hard one before. 58.3 something? 319. So the book has 58.33. I'm just going to do that for room's sake, okay? And then the answer here, I'm just going to have my students just put it up here, right here. But the answer to this, and it's 0.01. So that's nice, right? So what is it going to be? This is a great question for the AP test. Do you know why? Because what happens again, I'm going to say it clearly to the screen, to anybody listening, and to all of you. Do you get a calculator and a multiple choice? No. Can you do this without a calculator? Yes. I don't know if AP test writers are watching, but I guess this would be a good question then, right? Okay, let me know. Okay, so this is going to be 5.83. You can see maybe why I didn't even bother, because how many sig figs can we keep it? Oh, 2 over. Thank you. What was it? 58.3 then?
No, but then you go 2 decimal places over, you know?
Oh, what is the mass then? I'm just really making a mess here. Point. Okay, I'm going the wrong way. Thank you. I could say I'm just testing them, but really I'm just making mistakes. Okay. But those are people would probably do though. They'd do it the wrong way like I just did. Oops. I'm so sick right now. It's okay though. I just hope I don't strep. I hate strep throat. We're good for one part. That's a long question. Okay, so let's keep going. We need to keep some of these mole amounts though, all right? So what I'm gonna do is I'm gonna put underneath here some mole amounts we need to keep, okay? So what I'm gonna do, I'm gonna get rid of this for a second. And I'm just gonna recalculate some moles and just set them right underneath here, okay? So we have 0.02 moles of or 0.0, moles of KOH, okay? And then we only used, do we use all of it? Yeah, right, so this is our limiting. So we're just gonna write down some facts here. And then we had 0.02 moles of, 0.02 moles of MgNO32. You maybe don't know where I'm going with this. Some of you might know. Okay, and then this was our excess. And so we only used 0.01 moles of it. Hope some people kind of know where I'm going here. Okay, and then this was all about our product. So let's do the easiest one first, okay? Which of these ions, okay, and I always tell students, the one that's going to be 0 is the one that's in the limiting and it's in the precipitate. Because particulate-wise, draw a particulate view, okay? So they both were in little beakers to start with. Kind of go here and here. I think I can do this. Or little test tubes or whatever you had them in, okay? And so over here, now let's do dissociation. So inside of here, we won't draw what they look like, but let's put the quantity. So at 5.02 of this, do I get 0.02 of both of these? Right? So inside of here, I have 0.02 moles of potassium ions, and I have 0.02 moles of hydroxide ions. Now be careful. This is where life gets a little tricky. I'll talk about this in a second. We started out with 0.02 moles of magnesium nitrate, which meant that in here, I'm just going to do this first, 0.02 moles of magnesium we had. So let me write down the dissociation. This is where the question gets AP Chem. And in our first year Chem, sometimes we don't have time to do a question like this. So that's why I'm doing it now. So if I have 0.02 moles of this, are we all okay with that? It breaks into the same amount of magnesiums when they dissociate. Right? This is where the tricky part comes in. How many nitrates are there at the very get-go? It's kind of like an ice table sort of, because we've gone through this with, rice or reaction, initial, change, equilibrium. Some people do before and after, they call them BA tables, or a reaction before after. That's sort of what we're doing right now. So what do we have before? 0.04. Okay, now this is before we dump them together. So keep in mind, this is before we let these two react. So over here, let's draw who went where, okay? So this is where the particular views on AP test become very important. Who's down here? Like what went down into that area? Precipitated. The Mg and the OH, right? Okay, so down here are magnesium and hydroxide ions. They went there. And then who's up at the top, which we took out of the net ionic? So we took the net ionic and said, nope, you don't matter. We took you out. But let's not say that. So who's up here right now? K and NO3, okay? Now, they're kind of the easy ones besides whoever's zero. So let's do the 0 one first. Then we'll do the spectator second. And then we'll deal with the ion, write this down, the ion that's in the precipitate, but it's excess. What does that mean about that ion? So some of it went to the precipitate, but some of them didn't find a buddy to bond with, per se, and precipitate. This is why this is AP Chem and not first year Chem. So let's just do the one that we know is 0 and be confident they know which ion is in this beaker or this beaker, okay? And it went into down here and it found a precipitate buddy completely. The hydroxide, right? Are we good with that? So down here, this would mean that all the hydroxides are gone. That means they're not floating around up here. Are we okay with that? So it's in the limiting. So this sort of went to like 0. Got used completely. Okay. How can we probably prove that if you know acid, base, pH stuff from AP now? Let's do the rest of the ions. What are the ions that are left? Potassiums, right? Because they're spectators. Nitrates. Those are both from strong acids and bases if they were to dehydrolyze the water. Because what else is still in there too? Water. Okay. Who's the other leftover? Magnesium. Does magnesium bond to produce a strong base, meaning its hydrolysis reaction would be nothing? So what do we have in solution? All neutral species. So if you did this, could you prove that there's no acid-base properties in the upper layer? That's kind of a way to tie it into AP Chem. Is you could take some just pH paper and say if all the hydroxides are gone, they're not going to change the pH of the water molecules. Okay? Or the pH of the solution, I should say. All right. So that's just a little piece of advice for AP Chem since you know about acids and bases. At least I hope you do. Okay. So let's do the next one. Potassiums. What are we going to do? Here they are, right? So how would I find my molarity of my potassiums? What is molarity? Moles of something over the liters of that something. Are we okay with that? Okay. Be careful though. What is the liter amount they're going to be in? So I probably should have even drawn this like, I know it seems silly, but I probably should have drawn this to be more accurate. Like that maybe or something, okay? Because what's the total volume here, assuming volumes are additive? 200, right? So some of the stuff we kind of did with pH and titration curve calculations where we had to keep adding the volumes together to kind of find the molarity of the solution, what's in the flask. To do that, you got to be careful the flask holds 200 or the beaker, whatever we have. Okay, so that means down here, if I put that in liters, what is that in liters? 0.2 liters. Okay, so right now we have to say that right now it's a bigger pool. So just imagine if, like, I always tell my students, like, you had friends and you were at your smaller pool and then you went to somebody else's house that had a cooler, bigger pool. Well, then your concentration of you sort of is smaller per se because you have a bigger pool. Okay, so you're going to go into 0.2 size. What's the mole amount? 0.02. Uh-oh. Again, is this AP Chem no calculator? You betcha. I always tell students just move the decimals over. So like if we move this one over twice or we move this over once. So if we move it just once, it's 0.2 over 2. Okay. But some of you are going to just say, I don't want to do that. So you could do 2. So you'd have 2 over 20. I kind of like that better. Are you okay with this? These are this video I probably put in the description, some tricks to do basic math. Slide the decimal until you go, ooh, that's 1/10. I like that, And so if that's 1/10, then now you can hopefully put it back in a decimal. What is it? 0.1, right? Are we okay? Okay with all our calculators? So that means the potassium, right, is 0.1. Let's check. You guys keep going. See if you can do the next one without me. I'm just going to make sure we are on the right path with the answers. I actually didn't go rogue. A lot of times in class, I just make up a problem on the spot. I'm like, I don't care. This one I'm checking because I don't want to make a mistake. Is it? Yeah, we're right. Okay, here we go. Let's keep going. Let's do the next sign that I think is pretty easy. The nitrate. As long as you caught that it doubled. Is the nitrate in the same pool party? You betcha. So let's make sure we have labels here. Now, what was interesting about the nitrates? Like you had 2 friends. So we have a lot of twins in our building, and I think that's probably true with a lot of schools. We won't name, I don't know. Well, we can do the 2. I'll shout out to Isabella and Gabrielle. I won't say their last name. Okay, so they come together. Anybody that knows them knows that's actually a very true fact. I've never seen them ever in my 4 years of knowing them. You're right, 4 years. I've never seen them apart. It's weird. Okay. And if one shows up first, you know the other one's coming. You can hear them usually. So, hi, ladies. They're great TAs right now. So what are we going to do? We got to put both in there. So they're point what? 0.4. So I kind of like that, the other one. So slide it over twice to get 4 over 20. What is that? 1/5. Do you know what that is in a decimal? 0.2. Make a Quizlet about fractions turning back into decimals. Plus, you engineers, you're going to do good with that. Okay, here we go. That's NO3. Does that make sense that it's more? Think of the particulate view if you had to draw it. 0.2, right, Anna? Dean, are you going to judge my sig figs? Is that why you're looking at me like that? He should be, though. We can add an extra 0. Trailing zeros after the decimal count. Gosh, people just don't want to learn sig figs. Okay. Dane usually holds me accountable. He's like, if I'm on a week more, he's tired. Are you tired, Dane? I'm tired. Is this right, or are you just... Josh, how we doing?
I'm good.
He should have done a ton of this. He did a ton of math. Okay, when I met Josh, I looked at all his notes. I was like, wow, that's math. Okay, here we go. This is the hardest one, okay? Because let's just get rid of this guy. This all went in solution. What about the magnesium? Be careful, be careful. We had some, we used some. Easy numbers, though. So what do we have left? Be careful. What do we have left of the magnesium ions? So we had 0.02. We used, now this is 1-to-1. We used 0.01, right? So this is easy, I think. Let me get rid of this. So if you really want to show the work, let me slide this guy over here, gal over here. What in the world? That's too big. Mg2 plus. There we go, that's right. So if you really want to show it all, you had 0.02 moles of it, but then you use 0.01 moles of it. But what does that really mean? You left with 0.01. And you're going to put it in the 0.2. So that means in my little picture right here, I got to draw that there really are magnesium still floating up there. And so what's the concentration of them? 0.01 divided by 0.2. Sounds familiar, doesn't it? What is that going to be? So we have, if you move it over, you have 10 divided by Or should we just move it? Yeah, 1, 2, 10 divided by, I'm having a memory lapse here. What would you guys put? I'm like losing it now. Just do 1 over 20. Yeah, oh my goodness. I was going to do 10 over 200. I'm like, that's gone too far. 1/20th is? We don't know.
No, it's
0.05?
Yeah.
Okay, good. Where did they even have that one in here? Oh, yeah. We're good. Okay, now, little sig fig thing again. Trailing zeros after the decimal count. This is not a trailing zero, okay? These are trailing zeros. Yes, there's a decimal. Gosh, people get frustrated, and it's okay. So what do we usually do? We do that. Okay, 5.00 times 10 to the minus 2. AP test loves that too. They might even start with a question with that. Okay, I think that was hard. I think that was a lot, but I think that was good review. We have a precipitate reaction. We could even draw some particulate views. The big thing, don't forget that there are water molecules in here. There are cute little H2Os besides all these little ions, and then this would be trigonal planar. So you could do a lot of particulate views. You could do the size of the potassium versus the magnesium, which I think I might have messed up. So the potassium actually should be bigger, I think. Magnesium should be smaller. Well, I don't know, actually. That would be a tough one. I'm going to say they're actually probably pretty close. So you could do that. Now, remind yourself before you leave this chapter, you do need to know your ions. You do need to know your solubility rules. Of course, you're going to use a periodic table to get all the molar masses. On the AP test, I'll be honest with you, what kind of equation is going to be helpful for this? Honestly, I think they have like the definitions, or maybe there's a molarity somewhere. But really, when you try to look for this to help you with stuff that we did right now, it's not going to help you. There's nothing on that equation sheet that's going to be helpful. What you need to know is actually, these things I just showed you. Now, last couple videos, I'd also know the configurations of things. Josh might want one of these. And then again, they could get to Vesper because nitrate is a ion that is covalently bonded. So they could ask you the shape of that. All right, that is session, what was this, 5? And 6 is going to have to be super short. It's going to be PV/NRT or gas law stuff and maybe some solutions, but maybe not. I don't know. We might do like a vapor pressure or something, but we'll call that part of the gases. So we'll do a little gas law thing, make it quick. We're going to take a pretty good size break, I think, but we do need to be done. It's almost 10 before the normal school day starts. So thank you. See you later. We're going to take a break and hopefully smile and laugh because this has been serious business. However, this is a good invested time because you got to put the time in anyway for the AP test. I tell my students, you can't just study the night before. So if anybody watches this right now, and it is, what is it, May 8th is the day before the test?
Yes.
Good luck. I mean, that is not a good idea to study the night before. There's too much, okay? So you should be studying weeks before. That's what we're doing, okay? So if somebody watches this and it's May 8th and it's midnight, go to bed. You're like, I hope you're just doing a podcast of this, because you're going to be in trouble. Okay, bye. See you later. Good luck, though.